When the Hubble Space Telescope began releasing sharp color images in the late 1990s, NASA found itself with an unexpected kind of criticism. People said the photos looked fake. Alright, I think that's... When the Hubble Space Telescope began releasing its sharp color images in the mid-1990s, NASA found itself facing an unexpected kind of criticism. Instead of celebrating the detail, many people questioned the authenticity. Articles accused NASA of, quote, photoshopping space, arguing the images were too bright, too saturated, and too stylized. The colors simply didn't match what the people or the public assumed space should look like. To clear up the confusion, NASA released explainers emphasizing one point. The colors weren't mistakes, and they weren't added as decoration. They were part of the scientific workflow. The backlash revealed a broader misunderstanding of what astronomical images actually are. Most space images aren't photographs in the everyday sense. They're visualizations, translations of physical data into forms humans can comprehend. A telescope like Hubble or the James Webb Space Telescope does not capture color in the way a phone camera does. A phone camera has red, green, or blue filters built into a sensor, designed to approximate human eyesight. Space telescopes have a very different mission. They record radiation, light far beyond the range of human vision, ultraviolet, infrared, and extremely narrow emission lines from a specific atom or ions. A detector measures photons, converting arriving light into electrical charge. What comes out isn't a color image, it's a grid of numbers. And every exposure begins as a grayscale frame. A single pixel's brightness represents the intensity of light at one specific wavelength. To understand a nebula or galaxy, astronomers take multiple exposures, each through a different filter that isolates a tiny slice of the electromagnetic spectrum. One hydrogen alpha filter passes only light coming from ionized hydrogen. An oxygen 3 filter captures a narrow band around doubly ionized oxygen. Infrared filters on the James Webb Space Telescope isolate heat signatures from dust, molecules, and young stars shrouded in thick gas. Each exposure produces its own grayscale image, useful but incomplete on its own. Colors center later during processing. Astronomers assign a visible color to each wavelength, usually following a consistent theme. Longer wavelengths shift towards reds, shorter wavelengths towards blues, and intermediate wavelengths towards green or golds. When these layers combine, they form a composite image. The method is called representative color. It is a systemic mapping of invisible wavelengths onto visible ones. The purpose is not to produce literal realism, but to reveal structure. When each wavelength is assigned a different color, differences in chemistry, temperature, density, and energy become obvious at a glance. Without this mapping, most astronomical structures collapse into the same shade of gray. Dust clouds, ionized gas, reflection regions, and star-forming zones often overlap visually when stripped of color. Representative color separates them. It exposes shock waves, temperature gradients, filamentary structures, and the boundaries between stellar, nurseries, and older regions. It makes physical processes visible. The analogy is a weather radar. Red doesn't mean a storm cloud is literally red. It means something about intensity. Space imagery uses color the same way. This is why two teams can take the same data set and produce images that look different, yet are both accurate. One group might emphasize chemical contrast by stretching certain wavelengths. Another may choose a palette that highlights the temperature distribution. Another might aim for naturalistic tones to anchor viewers in something familiar. These differences reflect decisions about communication, not disagreements about reality. Behind the scenes, every scientific image goes through calibration steps. Dark frame subtraction, flat field corrections, cosmic ray removal, to ensure the numbers are physically meaningful. What varies is how to best visualize them. The confusion about scientific interpretation is nothing new. In 1976, NASA released the first color image of the surface of Mars. A calibration issue made the Martian sky appear blue. almost Earth-like. When corrected, the sky turned to its expected reddish tone. The underlying data never changed, only the interpretation. How the numbers were translated did. This underscores a fundamental point. Color in scientific imaging almost never records human vision directly. It organizes information. This also explains why images from the James Webb Telescope have such vivid palettes. The telescope sees exclusively an infrared light, which humans cannot detect at all. Every Webb image must be translated into visible color, and that translation carries scientific meaning. Longer infrared wavelengths tracing cooler dust and molecule clouds mapped to reds, shorter infrared wavelengths often tracing hotter stars or fine dust structures mapped to blues. What looks like artistic choice is actually a physical ordering, a chromatic representation of wavelengths we cannot see. A scientifically rigorous view also forces us to confront a more philosophical question. What would these objects look like if we were actually standing near them? The honest answer is very different. Human eyes cannot accumulate light over minutes or hours like a telescope does. So many nebulae appear brilliant, and images would be faint smudges or invisible entirely. Some color regions would appear washed out. Infrared-only structures would be completely unseen. Even the iconic pillars of creation would look much less dramatic without long exposure, imaging, and wavelength isolation. The colors in space images are not trying to show us what the universe looks like. They're showing us what it's made of, how it behaves, and where energy flows. The distinction between appearance and underlying structure connects to a long-standing philosophical tradition. Plato described a world where shadows resemble reality but never reveal it fully. Kant argued perception is shaped by the mind's built-in frameworks. We see not things in themselves, but appearances filtered through our conceptual structures. Nelson Goodman went further, suggesting that scientific representations don't mirror the world, but construct useful versions of it through systems, scales, and conventions. Representative color fits directly into this category. It is a translation system, a way of converting raw radiation into numerical arrays into a visual language that reveals the physics of distant objects. The colors in space images aren't fake, but they're not literal either. They're bridges between human perception and cosmic phenomena. They reveal patterns we otherwise would not detect. They show how matter itself organizes across vast, cold, lightless regions. They turn visible physics into visible form, and in doing so, they remind us of something essential. These images are not windows into a universe that looks like a rainbow. They're tools for understanding a universe that behaves in ways our eyes were never built to see. They're not showing us what space looks like. They're showing us what space is.